Hello, everyone. Welcome if you're new, welcome back if you're not. My name is Talia. I'm an incoming third-year student, that feels crazy to say, at UC San Diego, and I study chemistry and I minor in science education. This YouTube channel is an extra fun resource to help you reinforce your chemistry knowledge or get help with any topics you may be studying in class. Today, I am going to be finishing up thermochem by talking about potential energy diagrams and how to calculate things like the activation energy and the delta H for forwards, backwards, catalyzed, and uncatalyzed reactions. So if you need help with any of that, keep on watching, and without further ado, let's get started. All right. So like I said, this video is going to be about potential energy diagrams. I'm going to be looking at the slides on my iPad that you should be seeing on your screen. So I'm going to talk through them with you. Before we get started with a practice problem, I wanted to show you what a potential energy diagram for a reaction will look like and also go over some important definitions and terms that you might see in your problems. So on the right side of this slide, we have a potential energy diagram. This is specifically of an endothermic reaction, and I believe my example problem will be the same, but you can obviously have them for exothermic reactions as well. So we already know what reactants and products are from doing other chemical reactions. Reactants are your starting materials and products are your final materials. Our point of highest potential energy is our transition state or transition step, which is the in-between of the reactants and the products. So it's the point where the bonds of the reactants are breaking and the bonds of the products are forming. So it is quite literally a transition. We can also calculate a couple things from this graph. We can calculate the enthalpy change, which is what we've been doing throughout this whole unit of calculating delta H. But when you have a graph, you can determine the delta H from the potential energy of the products minus the potential energy of the reactants, since heat is energy. And that is the next bullet point. And then we also have a new thing called activation energy. And activation energy is the energy hump kind of that you need to get over in order to go from the reactants to the products. So it's, as you can see in green, it's from the reactants to the transition step. So that amount of energy. And then finally, it's not shown on this graph, but you can also have catalyzed reactions. And a catalyst is something you put into a reaction that speeds up the reaction. And it does this by providing an alternate pathway that has a lower activation energy. So you'll still have the same reactants and products, and those will still be at the same energies, but your activation energy will be lower. It's a smaller hump. So those are the main definitions. Also a note that is on the next slide, you can calculate the activation energy in delta H for forwards, backwards, catalyzed, or uncatalyzed reactions. So normally reactants are on the left and products are on the right, but sometimes you can have, you might be asked for the backwards reaction, and you have to pretend that the right side is the reactants and the left side is the products. And I'll ask some of those questions as well. So here's the example problem. I have a cute little potential energy diagram here. The uncatalyzed reaction is in black and the catalyzed reaction is in green. And I have 4 things you need to calculate here. So we're going to do one together, and then I suggest that you pause and try to do the other 3 on your own. So first we want to calculate delta H for the forwards uncatalyzed reaction. And we know that delta H is the delta H of the products minus the delta H of the reactants. So we look at where the products are. I would say that's 250 kilojoules because the products are on the right, as I put in that note. And then the reactants are on the left at 150 kilojoules. So I would say that the delta H for the forwards uncatalyzed reaction is 100 kilojoules. So now take a second, try to apply that math try to apply the definitions I've told you about to the rest of the problems. I know sometimes it can be a little bit hard to see where the graph intersects the numbers, but just try your best. All right, so let's quickly go over the answers. So we did part A. For the backwards reaction, it's just the same, but opposite. So we're now looking and saying that the products are on the left and the reactants are on the right. So we're going to do 150 minus 250, and that's negative 100 kilojoules. And it makes sense because the reactants and the products, like that part doesn't move. We're just flipping which one is which. The activation energy for the backwards catalyzed reaction. So we want to look at reactants on the right, and the catalyzed reaction is in green. So if my reactants are at 250 kilojoules and the highest point or the transition state is at 300 kilojoules, then our activation energy is 50 kilojoules. And then the activation energy for the forwards catalyzed reaction, we look at where the reactants are for the forward reaction, which would be on the left. And then the transition state is the same at 300 kilojoules. So 300 minus 150 is 150 kilojoules. So your activation energy will be positive because you're always overcoming a hump. But your delta H, depending on if your reaction is endothermic or exothermic, will be positive or negative. And so when we look at the forward reaction, this is technically endothermic because our products are higher in energy than our reactants. However, if we flip it and are looking at the backwards reaction and we say, okay, our reactants are on the right and our products are on the left, then our products are losing energy and therefore the reverse, the the reverse reaction is exothermic and therefore the sign will change for your delta H. So that wraps up our discussion on potential energy diagrams. I hope that helped. Next time I'm going to be jumping into a new unit, so stay tuned to see what that is. I haven't quite figured it out yet. If you have any questions or comments about this video or anything in general, feel free to leave them in the comment section below and I will do my best to answer them. I hope you enjoyed watching the video and I will see you in my next one. Good luck with learning chemistry.